Hello everyone, my name is Arjun and the title of today's talk is Mechanism of Dissimilar Heat Transfer Enhancement in a Laminar Channel Flow subjected to Wall-blowing section. There is a never-ending demand for improving the energy efficiency of thermofluid devices like heat exchangers, owing to its wide range of industrial applications. Now, for improving the energy efficiency of such a system, we need to aim at reducing the pressure loss and increasing the heat transfer. And they are respectively quantified using the non-dimensional parameter, the skin friction coefficient, and the standard number St. Thus, enhancing heat transfer while minimizing the pressure loss penalty is one of the ultimate goals in heat transfer research. But according to Reynolds analogy, a hypothesis based on similarity between heat and momentum transfer, any technique that aims at improving the heat transfer will also result in an increase in the pressure loss. Since Reynolds analogy is not based on any physical law, the natural question that we can ask is it possible to increase heat transfer without having a corresponding increase in pressure loss? Such a scenario, we call it as dissimilar control and can be quantified using the non-dimensional parameter called analogy factor A, which is defined as the ratio between standard number and skin friction coefficient. And dissimilar control is said to be achieved when the value of A is greater than 1. Our aim is to apply flow control techniques to increase heat transfer and reduce the pressure loss so as to achieve a value greater than 1 for the analogy factor. The existing flow control techniques can be broadly classified into passive or active techniques depending upon the need for additional energy to implement these techniques. The traveling wave like wall blowing section, which is used in the present study, is a typical example of active control strategy. Shown here is the plot of analogy factor versus Reynolds number for the existing couple of flow control techniques. And as you can see, almost all the existing passive control techniques result in a value much lower than 1 for the Reynolds analogy factor A. Whereas it has been established that a traveling wave like wall blowing section can achieve a value greater than 1 for the analogy factor, especially under turbulent flow regime. So the objective of the present study is to understand the dependence of heat transfer enhancement under laminar regime on traveling wave parameters and also to clarify the mechanism of dissimilar heat transfer using the idea of triple decomposition, phase analysis, and budget analysis. We consider 2D channel flow subjected to a traveling wave like wall blowing section where the traveling wave is characterized by its amplitude phi, wavelength lambda x, and phase speed up. The governing equations are the Navier-Stokes equation and continuity equation for velocity and the scalar transport equation for temperature. Here, Q in the scalar transport equation represents the heat generation term and we set it equal to the mean pressure gradient driving the flow. We also set the Prandtl number equal to 1 so that the governing equation for streamwise velocity and temperature has a similar form. The boundary condition for u and theta are set equal to 0 so that the boundary condition for the streamwise velocity and temperature also has a similar form. All the simulations under the present study are carried out at constant flow rate condition and at bulk Reynolds number equal to 100. Coming to the result, shown here is the contour plot of the analogy factor plotted as a function of lambda x, that is wavelength, along the y-axis and phase speed along the x-axis. As you can see, a value of a greater than 1 is achieved for phase speed ranging between up is equal to 0 and 1.5, and the maximum value is obtained for a lambda x up combination of 2 pi and 0.75, and hence this point will be used as the reference point for understanding the mechanism of dissimilar heat transfer enhancement. It is also worthy to note that while calculating the analogy factor shown here, the power required for driving the control input is also taken into account. For understanding the dissimilar mechanism, we first make use of the concept of moving average window and the idea of coherent components. Since our control input is in the form of a traveling wave, any flow variable can be expressed in terms of a new coordinate frame psi y, where the coordinate frame moves along with the traveling wave with the same speed up. Here, the new streamwise coordinate psi is given by x minus up into t, and psi is equal to 0 corresponds to the location where the wall suction is maximum. All the flow quantity in the new coordinate frame is termed as phase average quantity, and if we average them along the psi direction, we get the mean quantity denoted by f bar. The difference between the phase average quantity and the mean quantity gives us the coherent component. So we have a new coordinate from psi y, and any flow variable can now be decomposed into its mean component and coherent component. Here, the coherent component represents nothing but the fluctuation in the flow variable that are in coherence with the applied traveling wave. Shown here is a contour plot of the wall normal velocity and temperature, that is V tilde and theta tilde, for the bottom half of the channel, for the reference case of lambda x UP is equal to 2 pi and 0.75. As you can see, psi is equal to 0 corresponds to the location where the wall section is maximum. Now, in order to explain the theta tilde contour, that is the temperature contour, we have plotted the phase average velocity on top of the theta tilde contour. We can identify three characteristic features. First, the downwelling motion due to wall section above psi is equal to 0 brings in high temperature fluid very close to the wall, resulting in positive contours for theta tilde above psi is equal to 0. And the reverse happens above the locations of maximum wall blowing, that is for psi is equal to minus lambda x by 2 and plus lambda x by 2. Secondly, the wall movement at the speed of minus up drags the theta tilde contours in the upstream direction due to the viscous effect. And finally, the convection outside the near wall region transport the temperature fluctuation theta tilde in the downstream direction. As you can see, the upstream fluid motion close to the wall and the downstream fluid motion away from the wall results in circulation rows, as can be seen from here. Coming to the U tilde contour, the favorable pressure gradient generated above psi is equal to minus or plus lambda x by 2 and adverse pressure gradient generated above psi is equal to 0 results in fluid acceleration and deceleration in the upstream and downstream direction of psi is equal to 0. The absence of such a mechanism for theta tilde makes its response quite different from that of U tilde, which becomes further apparent from the distribution of the theta tilde minus U tilde contour, which eventually leads into large dissimilar heat transfer enhancement. To understand how this large theta tilde minus U tilde eventually leads to dissimilar heat transfer, we can make use of the Fukugata-Iwamoto-Kasagi identity, or commonly known as the FIK identity. We know that for a non-controlled laminar channel flow, skin friction coefficient CF is inversely proportional to Reynolds number. Now, using the FIK identity, the increase in skin friction coefficient on applying the control input can be written like this, where the additional term consists of the y-weighted Reynolds shear stress. For standard number, a similar expression follows, where the second term is given by y-weighted scalar heat flux. The difference between these two quantities, termed as dissimilarity, is given by the difference between y-weighted scalar heat flux and Reynolds shear stress. And in terms of the coherent components, we can write it like this. So what we are interested is in the correlation between theta tilde minus U tilde and that between V tilde. The plot of this quantity in the psi y coordinate is shown here, which on averaging along the streamwise direction psi gives the wall normal distribution of the dissimilarity D. And as you can see, maximum dissimilarity is observed very close to the wall between y is equal to minus 1 and y is equal to minus 0.4. Now, the importance of the induced pressure gradient on the generation of dissimilarity can be understood from the budget analysis. As we have seen earlier, using the FIK identity, we can write the dissimilarity as the difference between y-weighted scalar heat flux and Reynolds shear stress. So we are interested in the budget of scalar heat flux minus Reynolds shear stress. The budget consists of 5 terms: the production term, the 2 diffusion term, the pressure temperature velocity correlation term, and the dissipation term. And each of these 5 terms for the reference point of lambda x sub is equal to 2 pi and 0.75 are shown here. As you can see, the pressure temperature velocity correlation term act as the dominant term between y is equal to -1 and y is equal to -0.4. This is the same region where we have observed large dissimilarity as well. Now, from the distribution of the two terms that constitute the pressure temperature velocity correlation term, we can see that the second term acts as a source term for dissimilarity. So the correlation between wall normal velocity and the induced pressure gradient in the streamwise direction act as a source term for dissimilar heat transfer enhancement. Whatever we have seen so far can be schematically outlined as follows. The wall blowing end section creates a favorable pressure gradient above psi is equal to plus or minus lambda x by 2 and an adverse pressure gradient above psi is equal to 0. The resulting positive minus v tilde into dou p by dou x term results in positive large dissimilarity around both blowing as well as suction region. Thus generated dissimilarity get redistributed in the near wall region due to the circulation rolls created due to viscosity. Coming to the summary of the present study, what we have shown here is that in a laminar channel flow, dissimilar heat transfer enhancement can be achieved using downstream traveling waves, and maximum value for the analog factor occurs between up is equal to 0 and 1.5. And dissimilarity between momentum and heat transfer is caused by the pressure fluctuation arising from the continuity constraint. Thank you for your kind attention.